Hi, in today's video we will finally be able to prove the full version of the Hochschild-Rosenberg theorem using the machinery of non-abelian derived factors and animations of one categories. So something we will encounter along the way is the cotangent complex, which we will see as the non-abelian derived factor of Kähler differentials today. And we will study that in today's video and the following video a little more. I'm Achim Krause from Mathematics Münster. In our lectures on the basics of infinity categories in higher algebra, you can find a great video on non-abelian derived factors. In that we introduce the notion of animation, which will be relevant to our proof of the HKR theorem today, and also the construction of the cotangent complex. So I'll only briefly review that here. If you want, check out the longer detailed video by Thomas on this. The idea is that we start with a one category C, which is generated by compact projective objects. So here K is called compact projective if mapping out of K commutes or preserves filtered colimits. This is what it means to be compact, and Hom out of K also preserves reflexive coequalizers. By reflexive coequalizers, we simply mean diagrams of this shape, where you have two objects, two parallel arrows, but then one arrow in the other direction, which is a section to the other two. So both composites I can form like this are identities. And this is simply the bottom two stages of a simplicial diagram. That's where this comes from. And note that here we really mean Hom taking values in sets. So this condition only makes sense if we are in a one category. So in particular, if you wrote down the same condition for the infinity category, which we get as the nerve, then this would typically not hold anymore. So here it's important that we start with a one category. So this is what it means to be compact projective, and then being generated by those means that Hom out of K detects equivalences where we let K range over all compact projective objects. So in other words, this means that a morphism in C is an equivalence if and only if an isomorphism if and only if it induces an isomorphism on Hom out of K for every K, for every compact projective K. And I guess sort of implicitly part of my assumptions on C is that it has all those colimits. So in that situation, we can pass from C to its full subcategory of compact projective objects. So if you do this, for example, to the category of all sets, then this is satisfied and the compact projective objects will be precisely finite sets. Or if you do this to all R modules for some ring R, then it will turn out that compact projective objects are actually precisely the finitely generated projective modules. So we can take the full subcategory on those objects, and then we can construct an infinity category out of it, the animation of C, which Thomas describes in the video on non-abelian derived functors explicitly as product-preserving functors out of the opposite category of this full subcategory of compact projective objects. So in here I have coproducts, and after op I have products. And so this is an explicit construction, but how you should think about this maybe is that this category has a certain universal property. Namely, it's an infinity category which contains the compact projective objects of C as a full subcategory, namely via the Yoneda embedding. But then it is somehow generated by those freely under filtered colimits and geometric realization of simplicial diagrams. So let us spell this out. So first of all, CP is a full subcategory of this category NMC. So this really means that somehow between those objects, the mapping spaces that I get a priori are discrete. And we also, so I said that these generate everything under filtered colimits and geometric realizations, but if you just close them under filtered colimits, then you see that the int category of compact projective objects also sits in here as a full subcategory. And then general objects, so we also need to involve geometric realizations. General objects can be represented as geometric realizations, and if I haven't said that yet, geometric realization in an infinity category means a colimit of a simplicial diagram, so of a diagram indexed over the category delta op. So general objects can be represented as geometric realizations of simplicial diagrams with entries in this subcategory int compact projective. And how should you think about mapping spaces? Well, as I told you up here, somehow these two one categories really sit in here in a fully faithful way. So between those objects, you somehow don't have any non-discrete mapping spaces. All the mapping spaces between them are discrete. So think of those as somehow the discrete objects in here. But then, in general, maps are more complicated. And since compact projective guys generate this, let's just describe the following special case where we map out of a compact projective object X, so an object coming from this Yoneda embedding of CCP, into a general delta op indexed colimit of some objects yj that lie in this int category. And then the property that sort of nails down these mapping spaces is that these objects X are still compact projective in this infinity category, but now in the infinity categorical sense, which means that mapping out of them commutes with filtered colimits and geometric realizations. So what this means is that this mapping space is actually colimit over delta op of the mapping spaces from X to these Yj. And now you'll notice that here, both of these guys are now discrete, right? We said the Yj come from this int category. So this is really a simplicial diagram of sets now. And so you see here how somehow these still have discrete mapping spaces with them, but here you can pretty much get arbitrary colimits of simplicial sets, right? And so that gives you the geometric realization of that simplicial set as an object of spaces. So this is where somehow the non-discreteness comes from here. And one example, of course, is if C is given by sets. In that case, well, product preserving functors out of finite sets op turns out to be really just be like functors, like these functors are precisely determined by what they do on the point. So in the case of sets, you get spaces. And the analogs of these things would be, like this would still be finite sets considered as discrete spaces, and this would be arbitrary sets considered as discrete spaces. And then you see how, of course, if you map out of something into, even out of a set, out of a discrete space into a general space, then you have a non-trivial mapping space, like a non-discrete mapping space there. And another example that Thomas discusses in the video on non-abelian derived functors is how the bounded derived category is an instance of this. So it turns out that if you have an abelian category which has enough projectives, then somehow these, maybe I'm forgetting some, yeah, which has enough compact projectives, maybe I should say, then this is satisfied. And you should maybe think of the example where A is just modules over a ring. Then compact projective objects are really finitely generated projective modules. So in that case, the bounded derived category is actually equivalent to this infinity category, or sorry, the non-negative derived category is equivalent to this infinity category animation of A. And again, you can think out what these examples here do for you. This is finitely generated projectives considered as a full subcategory of your derived category. This is just all projective modules. And then here, well, this tells you that if you map out of a projective into some complex of projectives, then you get this funny colimit, and then this is not just a simplicial set in that case, it's even a simplicial abelian group, and so you get somehow this space corresponding to the actual mapping complex. So in that case, you really get these mapping spaces that we know appear here by our other construction of the derived category. So the advantage of this description over the other one is that this is really functorial in any functors between A, right? If I have any, like this animation is completely functorial in arbitrary functors between one categories, maybe preserving compact projective. Right, no, sorry. So I guess, no, I should say this differently. The advantage is that somehow describing functors out of this requires less structure, because this is, as Thomas explains in the other video, the universal category that somehow obtained from this CCP by adjoining filtered colimits and reflexive coequalizers. So functors out of this anim A, preserving filtered colimits and geometric realizations, are the same as just functors out of the one category of compact projectives. So to see this universal property in action, for a non-additive functor from A to B, two abelian categories, we get a functor from A to B and then further to the animation of B. Right? We always have a restricted Yoneda embedding that goes from C into this entire thing, just by mapping compact projectives into them. And so this is just some functor, but we can uniquely extend that to filtered colimit and geometric realization preserving functor between the animations. And so here you get this non-abelian version of derived functors that doesn't make sense if you start with chain complexes to begin with. And as an example of how that works, because it's really easy to get confused here, let's see one example of a non-additive functor between abelian categories in action, and let's see what we get there. So for a commutative ring, we have a functor from the category of R modules to the category of R modules, which is like the nth exterior power. For example, you can define this by writing down the functor that defines an exterior algebra on an R module. Right? You just start with your R module, and then you form the tensor algebra, and then you quotient by all squares. So that makes it anti-commutative, and then this is just going to be the degree n summoned. So by this construction over here, this is of course very non-additive. For example, lambda 2 of a one-dimensional, of a rank 1 free module is just 0, like you would expect, but lambda 2 of a rank 2 free module is going to be a rank 1 free module. So this is not additive, but by this construction we still get a functor L lambda n from the bounded derived category to the bounded, from this non-negative derived category to itself. And so how does this work? Right, you're used to know to somehow left derived functors being computed on modules by picking a projective resolution, a chain complex of projectives, and then applying the functor level-wise and then seeing what you get. But the trick here is that we don't use chain complexes at all. Somehow chain complexes have additivity built in some way. What we really want is we want to look at these simplicial diagrams. So this is computed by representing objects by simplicial diagrams of projective modules. And then level-wise applying the functor. So for example, we could ask, in the case where r equals z, what does this do to the object of the non-negative derived category, which is just given by z mod n in degree 0, right? That's a chain complex over z, but it's of course not projective. It defines an object in here, but how would I write that as a simplicial diagram like this? So a projective resolution in the realm of chain complexes you would just get by looking at this two-stage complex with just multiplication by n as a differential. It turns out one way to get a simplicial diagram of projective modules which realizes to, like, which has underlying chain complex equivalent to z mod n, would be by taking this and applying the Dold-Kahn correspondence to it. So at this point, I want to pose as an exercise to look up how the Dold-Kahn correspondence works, and then verifying for yourself that the simplicial abelian group applied, the simplicial abelian group corresponding to this chain complex actually looks like this, and to work out what the maps are. So, and then computing what L lambda n r gives us. So I'll sketch this here without talking about the maps, but the idea is now that you can apply this lambda n sorry, in this case I want to talk about lambda 2, sorry. So in this case, lambda 2, applying this level-wise, gives us something that starts with these terms, and then actually, as I said previously, lambda 2 of a free rank 1 module is just 0. Lambda 2 of a free rank 2 module has rank 1. And then I guess in the next stage it will have rank 3, and it behaves kind of funny, but it's certainly not additive. And so what you get here is this interesting simplicial abelian group, which is like rank 1 here and rank 0 in degree 0 and so on. And it turns out that this actually, if you run the computation, is equivalent to the object in this non-negative derived category, which has just homology z mod n in degree 1. So it behaves in a very interesting way, and it's certainly not what we would get if we just applied lambda 2 level-wise to our projective resolution over here. And that's of course because, So what we've used here to get to the world of simplicial abelian groups and back from simplicial abelian groups to chain complexes, what we've used there is the Dalt-Kahn correspondence, and that involves direct sums. So somehow your functor only commutes with that construction if it is additive. Right. So try to get a feeling for what's going on here. Maybe it's not easy to compute all the homology of this, but maybe the first one, and see how this funny degree shift happens. And yeah. So at this point, of course, we can also apply this to a category that's not even an abelian category to begin with, right? I guess we have talked about the case of sets, but another interesting thing is the category of rings, right? That's not an abelian, or commutative rings. That's not an abelian category. So what does the animation of that look like? Well, the animation of the category of commutative rings, by definition, it's this category of product-preserving functors from compact projective objects op into S. And it turns out compact projective objects are the same as, in commutative rings, are the same as finitely generated polynomial rings. So, over the integers. So, we can write this more explicitly as finitely generated polynomial rings op. And this full subcategory of discrete objects that I get as ind of the compact projective objects in this animation, that's, as you might expect, just the category of all polynomial rings over the integers. So you can think of objects as represented by simplicial diagrams of polynomial algebras, polynomial rings. And how do mapping spaces work? Well, by a special case of the general behavior that we discussed, mapping out of a polynomial ring in a single generator, where we have some colimit over delta op of some polynomial rings yi, that gives us just the colimit over the respective sets of maps from here to here. So sorry, this is an animated C ring. And so what's the set of maps just of rings, z adjoint x to y to yi? Well, that's just the underlying set of yi. So here I just get the colimit of the simplicial diagram of sets yi. And so what we see here is that in this world of simplicial commutative rings, mapping out of a polynomial ring in one generator into such an object kind of extracts the underlying simplicial set. And of course, the underlying set of a ring is still an abelian group, so the underlying simplicial abelian group. So you can think of objects in this funny world NMC ring in this animation of commutative rings as some kind of fancy version of non-negative complexes with some kind of ring structure. It's not the same. There's also a way to talk about commutative rings in the infinity category DZ, and that does not agree. So it's a little misleading to think about this as a complexes with extra structure, but maybe that helps psychologically. And so the universal property of this animation, let's put that explicitly on the board again in this case, because we're going to use that for a number of different constructions, is that functors out of animated commutative rings, which preserve geometric realizations and filtered colimits, are just the same as functors out of polynomial rings, finitely generated polynomial rings into D. And there's another version of this universal property that's also immensely helpful, which is that functors out of the finitely generated, of the compact projectives, which just preserve nothing, no property, are the same as filtered colimit preserving functors out of IND. So in this case, out of the category of all polynomial rings. So what does it mean to define a non-abelian derived functor in this world of rings? Well, we have to specify either a functor on finitely generated polynomial rings, or what's somehow often more useful in practice is we start with a filtered colimit preserving functor out of all polynomial rings. And then that extends somehow in a unique way to a functor between these infinity categories, which preserves geometric realizations in addition. And of course, the recipe, how do you compute on a given object what that functor does? The recipe is, of course, again, starting with any object in animated rings. It can be described by such a simplicial resolution, right? A simplicial diagram of polynomial rings. And then you just level-wise apply this functor. That gives you some simplicial diagram in this infinity category D. And then you take the colimit there. So for example, if we go here into some derived category, the colimit you should typically think about as some kind of total complex of the simplicial diagram. And of course, one particular class of objects that we want to apply this to in here, right? We don't maybe have many natural examples of objects in here at this point, but one particular class of examples in here is the objects that come from the restricted Yoneda embedding from all of C ring, right? If I have an object of if I have a commutative ring, which is not polynomial, I can still get an object in here by just recording all the maps out of polynomial rings, all the sets of maps from polynomial rings into my ring. That gives a perfectly fine object in here. And to evaluate such a non-abelian derived functor on that means that I have to simplicity resolve my ring by polynomial rings. So I have to write down a simplicial diagram of polynomial rings whose geometric realization or whose underlying simplicial set is really just equivalent to the discrete simplicial set R. And then I level-wise apply my functor. And I claim we have already encountered one example of a functor in here, and that's Hochschild homology. So Hochschild homology relative integers That, of course, defines a perfectly fine functor from polynomial rings to the derived category of the integers, even the non-negative derived category of the integers. Right? We just gave an explicit construction, and we had to do some ad hoc resolving stuff in the non-flat case, but for rings that were flat over the integers, in particular polynomial rings, we just explicitly wrote down a complex, which is even factorial, was even factorial as a functor into just the one category of chain complexes. So that's the functor we're looking at here. And that commutes with filtered colimits. And so it extends to a functor from animated rings, animated commutative rings. Maybe call that LHH temporarily to the non-negative derived category. And it turns actually out that on commutative rings, if you give me an ordinary commutative ring and you put it in here via this restricted Yoneda embedding, then on these, this agrees with our previous definition of Hochschild homology. And note that our previous definition of Hochschild homology, where we said that somehow it a priori depends on a choice of flat DGA that resolves R, and then we checked that it gives it's independent up to quasi-isomorphism. That isn't quite enough to see that you actually get a functor out of commutative rings to this infinity category, DZ. A priori, there could be higher coherence problems. But here we really see that we get a functor from this universal property, and it extends what we previously did. So what's the idea here? Well, if you go back to our first videos on Hochschild homology, we checked actually there that if you have a simplicial commutative ring and you compute Hochschild homology level-wise, then and then take the total complex of that. So if you take the cyclic bar complex level-wise and then take the total complex of that, then that's the same as if you take Hochschild homology of the underlying DGA of your simplicial commutative ring. And so if you give me an ordinary ring and you resolve it simplically by polynomial rings, and then level-wise take Hochschild homology and then the total complex, right? That's exactly what we said the recipe is to compute these non-abelian derived functors on general commutative rings, which are not polynomial. Then we saw earlier that this actually gives something that's quasi-isomorphic to just Hochschild homology of the underlying DGA. And so if you resolve the original ring, then the underlying DGA is just quasi-isomorphic to the original ring, concentrated in degree 0. So everything fits. In other words, we knew already that Hochschild homology, the way we defined it, commutes with geometric realizations. Okay. So we will later see that there's a different way to get a fully factorial functor Hochschild homology in infinity categories in even higher generality. You don't need animated rings for that. You can get by with much less. But it's kind of nice to see that this non-abelian derived story gives us another way to very naturally derive the Hochschild homology construction. And so now the question is, we've seen already that we can compute Hochschild homology for polynomial rings via the HKR theorem. Can we also somehow extend the statement of the HKR theorem to general rings with this machinery of non-abelian derived functors? So the HKR theorem, of course, was only an isomorphism between a certain graded commutative ring and the homotopy group, or the homology groups of Hochschild, like the Hochschild homology groups. So how can we phrase that in somehow a more structured way about the functor Hochschild homology, taking values in the derived category? Well, something which you can generally do in the derived category, let's say of the integers, so for some object C in dz, think of it as represented by some chain complex, we can sort of cut off the homotopy groups one at a time. And so what the homology groups, sorry. So what this means is that we have another object, which I'm going to write tau bigger or equal n C, which comes with a map to C, which is an iso on Hi for I bigger or equal n. So this guy has the same homology groups as C in degrees bigger or equal n, and it comes with a map that witnesses that. And its homology in degrees below n for all I smaller n, its homology is 0. So one way to do that, for example, is you can start with your chain complex. Then you can get rid of all the groups below degree 0, below degree n. So that almost does the right thing, right? Then it definitely has 0 homology. By get rid, I mean put zeros there instead. So then the homology in degrees below n is certainly 0. The homology in degrees strictly bigger than n is definitely unchanged. The homology in degree n might have become bigger, right? Because suddenly everything is a cycle. Previously, not everything was a cycle. So to fix that, you replace the group in degree n by the subgroup of things that were cycles in the original chain complex. So every group below degree n becomes 0, the group in degree n becomes replaced by the cycles, and the groups in higher degrees are unchanged. So that's one way to think about this, but in fact, this construction comes even with this tau bigger or equal n even defines a functor from dz to dz, and you get a natural transformation like this. And you can get that out of universal properties, right? We constructed this as a certain localization of something, so you can actually make the definition I gave just now in terms of chain complexes functorial using this localization description of dz. But as an exercise about adjunctions, you might want to think about how to get this functor tau bigger or equal n from the adjunction to the inclusion of a certain full subcategory of the derived category. And that's a very illuminating exercise. Sorry, as the right adjoint, to be precise. Okay, So we have all these tau bigger equal n's of C. They're all given by cutting off the homology groups below a certain degree. And so in particular, we also get a map between tau bigger equal n plus 1 of C and tau bigger equal n of C. Right? This is, from this one, I get this one by just cutting off one more homology group. And now I can ask, what's the cofiber of this map? And since for a cofiber sequence, you have long exact sequences on homology, it's not hard to see that here you get actually a complex which just has a single homology group, namely the nth homology group of your original complex in degree n. So I'm going to write that like this. This means I have this complex, just the single abelian group HNC, and then I'm going to shift it to degree n. This is the complex that just has HNC in degree n. And so one way to think about what's going on here is that this defines a kind of filtration on my object C. Right? I have this sequence of things that all map to each other. And then the associated graded of my filtration, you have to be a little bit careful there because they're not really sub-objects and you can't really take quotients, but we can take quotients in a derived sense. Just take the cofiber. So if you understand that by associated graded objects, then somehow the associated graded objects of your filtration all live in a single degree. And so somehow knowing the homology groups of your complex precisely corresponds to knowing the associated graded of that filtration. And so in particular, in our example of Hochschild homology, we have for polynomial rings R, this tower, or this filtration, that starts with tau bigger equals 0 of the Hochschild complex. Right, that's just the entire Hochschild complex. But then you get all these stages that just cut off more and more of the homology groups. And if I also draw in to the right somehow the cofibers, here, for example, I get this single cofiber between degree n and n plus 1, then this is just going to be the nth homology group. And we know that somehow the nth homology group for polynomial rings, by the version of the HKR theorem that we already proved, the Hochschild-Kostan-Rosenberg theorem, we know that this homology group is really the nth, like the degree n de Rham differential group, right? The nth exterior power of Kähler differentials, considered as a complex concentrated in degree n. And so rather than trying to prove HKR directly, we can just take this whole diagram, all of these are functors, and we said that this one, for general rings, is already somehow non-abelian derived. In other words, Hochschild homology is the geometric realization preserving extension from what it does on polynomial rings. But all the others might not, right? So we can see what we get by non-abelian deriving all these functors, and in particular these. And so for a general ring, or even for animated rings, we define the nth HKR filtration on Hochschild homology as a factor from animated commutative rings to dz bigger or equal 0, which is the non-abelian derived factor, or I guess geometric realization preserving extension from polynomial rings or finitely generated polynomial rings. I guess either way, you have to check at some point that everything here commutes with filtered colimits, so that somehow these guys are, oh sorry, as geometric realization preserving extension from of the factor tau bigger equal n HH rank from, let's say, poly. You could also say it's a geometric realization and filtered colimit preserving extension from finitely generated polynomial rings. It turns out that this factor on polynomial rings, these factors already commute with filtered colimits, and that's simply because somehow filtered colimits preserve homology groups. So you can see that somehow there nothing changes. Okay. But here we get something more interesting, because, so what is the analog of this cofiber sequence? So it turns out that if you non-abelian derive a cofiber sequence of functors, then you still have a cofiber sequence, because this involves colimits, right? It involves geometric realizations. So what's this cofiber sequence here? It's going to involve the n plus first filtration, HKR filtration, the nth HKR filtration, and then it involves the non-abelian derived functor of this one. So I'm going to write that as L omega n R mod z, and then shift it to degree n, right? Omega n gives you a functor from commutative rings to, say, abelian groups. And we can, of course, restrict that to finitely generated polynomial rings, and then extend using sifted colimits and geometric realizations, filtered colimits and geometric realizations, sorry, to animated rings. And then we land in this world of complexes, right? So for any given ring, so we can evaluate that on animated rings, but in particular on just ordinary rings. For any given ring, this is going to be some complex, and then this notation just means we shift it up by degree n, because since we did that here. And now the question is, what does this still tell us about the Hochschild homology groups? And not everything is lost. So one particular lemma that we can directly see is this was somehow a filtration where we cut off one homology group at a time. These non-abelian derived functors, these still have the property that they only have non-trivial homology above degree n. So One way to say this is that the nth filtration is really in dz bigger or equal n. It's really a complex with homology vanishing in degrees below n. And the proof, just going to say that verbally, the proof is really just the observation that this is true if you plug in a polynomial ring. Right? By definition, this, for a polynomial ring, I just get this tau bigger or equal n of Hochschild homology. It's definitely concentrated in degrees bigger or equals n. And then we extend via filtered and via filtered colimits, via geometric realizations. But it turns out that this one is closed under colimits. Right? This is a subcategory of dz which is closed under colimits. For example, because it's closed under coproducts and pushouts. It's not hard to see. Okay, so these still somehow are concentrated in degrees bigger or equal n. So what about this guy? How does this guy look like? So one thing that you might be used to from usual derived functors is if you start with, say, a right exact functor and you left derive it, then the zeroth derived functor is just the functor you started with. So something like that happens here too. Namely, if you start with a functor from commutative rings to abelian groups, and this commutes with reflexive coequalizers. If you remember, these are colimits of diagrams that look like a coequalizer diagram with a section. Then the zeroth homology of the complex I get by taking the non-abelian derived functor of f and applying it to an ordinary ring R. Right? I can consider an ordinary ring as an object in animated rings. Just coincides with the value f took on R. And the idea behind the proof is, let me write that down. So we resolve R as a simplicial diagram of polynomial rings. Right, so this is a simplicial diagram whose underlying simplicial set, like it comes with a map to R, and on underlying simplicial sets, we get that the simplicial set of this guy is homotopy equivalent to just the discrete simplicial set on R. But then one can check from there that this, or say that R is the coequalizer, the reflexive coequalizer, the colimit of this part of my simplicial diagram in both sets, but then it turns out also in commutative rings, right? So this is a reflexive coequalizer, and now this non-abelian derived functor is computed by applying just f level-wise, and then taking the colimit of the resulting diagram in the derived category. So taking the total complex. So what does that mean? Well, LFR is the total complex of FR0 FR1, etc. And the zeroth homology of the total complex of such a simplicial diagram is the same as just the reflexive coequalizer of its bottom two stages. So to get a feeling for what's going on here, you should try to do the following exercise. So we want to apply this now to the functor omega n. The claim is the functor omega n from commutative rings to abelian groups commutes with reflexive coequalizers. And it's a little tricky to do sort of in one step, but there's a number of steps you can do. You can first check that the functor from commutative rings to sets, which sends a ring to an n-fold Cartesian product of its underlying set, commutes with reflexive coequalizers. And then that the functor from sets to abelian groups, which passes to the free abelian group, commutes with reflexive coequalizers. And then finally, that you can write omega n as a co-kernel of a map between things that you get by combining the first two steps. And the last thing is much easier to see if you just think about the definition of omega 1 first in terms of generators and relations. Okay, so we previously proved a very restricted version of the HKR theorem, which just worked for polynomial rings. We called that, so that was in one of our first lectures. We called that the version 1 of the HKR theorem. So let's now give version 2, which uses the following assumption. If the non-abelian derived functor of omega n applied to R is concentrated in degree 0 for each n, right? This is some object of the non-negative derived category, so what I want here is that its homology is concentrated in degree 0. There's no higher homology. Then HKR holds for the ring R. Right? We saw in our first discussion of the Hochschild-Costa-Rosenberg theorem that you always have a map from omega n to the nth Hochschild homology group. And then by HKR holds, I just mean that we have an isomorphism. Okay, so the idea is to exploit our filtration. Right, so we say we have a long exact sequence on homology associated to these terms. And I guess I'm abbreviating here a little bit. Of course, I mean Fn HKR Hochschild homology of R relative Z, but the ring is fixed and there's no possible, like in this proof, the ring is fixed and so there's no possible way to confuse things. Let me abbreviate like this. So we have this long exact sequence, and now note that we've seen earlier that the homology of this guy starts in degree n. The homology of this guy starts in degree n plus 1. And, oh sorry, I had forgotten the shift. And the homology of this guy also starts in degree n, because this guy is a non-negative complex, and then I shifted up by n. So what happens on Hn? Well, on Hn, I just see that this map is an isomorphism. So this long exact sequence shows two things. First, the nth homology group of this Fn guy agrees with the nth homology group of this. Minus the shift, it agrees with the 0th homology group of this. And then by the lemma we just proved, and the claim that that omega n satisfies the assumptions, this nth homology group is really just omega n, right? So that's the first thing we get. And then we haven't really exploited that we assumed that this is concentrated in degree 0, right? So that part always works. But now if this is concentrated in degree 0, then this guy is concentrated in degree n. And so you see from that that on all other homology groups, this long exact sequence just tells you that this map induces an isomorphism, right? So for all I that are bigger than n, this map is an iso. And so somehow we're again in this situation that this filtration really behaves like I'm just forgetting one homology group at the time. And so how do we finish from there? Well, of course, we know the nth homology group of Fn, and then the lower, it's just omega n. And then the lower property tells us that if we go from Fn to Fn minus 1 to Fn minus 2 and so on, it doesn't change anymore. And what is F0? Well, F0 is just Hochschild homology. So we get a chain of equivalences where this is the nth homology group of my Fn, but then it's also isomorphic to the nth homology group of F0, and that is just the nth homology group of the Hochschild complex, right? So the nth Hochschild homology group. Okay. Technically, we've only shown that under these assumptions, there is some isomorphism between omega n and Hochschild homology. By carefully thinking about multiplicative properties, one can actually check that this isomorphism here is the map that we saw in an earlier lecture we always have from omega n to the nth Hochschild homology group, right? That somehow used that we have a completely natural, like a canonical isomorphism between omega 1 and HH1, and then that the target has a multiplicative structure, and so it extends over these exterior powers. And so somehow by thinking about compatibility with the multiplicative structure, one can actually check that this isomorphism is the one that we previously saw. All right. So let me clean the board. So the remaining question, of course, is how can we ever hope to check the condition that went into the Hochschild-Costan-Rosenberg theorem version 2? Right? It's kind of, we're requiring for every n to check that the higher derived, like the non-abelian derived omega n has no higher homology groups. That sounds like an awful lot of work. So can we characterize that better? And we will actually need a slightly different description of this derived omega n. So let us black box this. This will be explained a little bit better in the next video, where we more closely examine the so-called cotangent complex. So let's just do a black box, namely that this L omega n R relative C agrees with the value on the object R of the non-abelian derived functor. And now we go from not the animation of commutative rings, but of commutative rings together with a map to the ring R, and then further to the bounded derived category, the non-negative derived category of R. And then, of course, we can forget further down to just derived abelian groups. Right? Our original thing only took values in derived abelian groups, so if we say that it agrees, then we have to go into the same thing. But the takeaway will be that this guy actually lifts naturally into this category. And what's this functor going to be? Well, the functor is going to send a polynomial algebra with map to R. So there's a little bit to think about, which is that the compact projectives in this one category are really, again, polynomial rings over the integers, but now with some map to R. So this is where I take my A from, and then the functor I want to non-abelian derive takes this again to omega n, but now omega n is an A module, I want an R module, so I base change to R. So this is our black box, right? It's not immediately obvious that this defines the same thing, because a priori, the way we defined this, we say that starting with the ring R, you have to write down a simplicial polynomial resolution and then just apply omega n. Just look at the abelian group omega n level-wise and take the total complex. Here we're looking at the same thing, but then we're also, in each degree, base changing this to R again. So it might even be surprising that this agrees, but it turns out this gives the same thing. And this description has the advantage that it's a priori endowed with an A module structure, with an R module structure. That is totally not obvious from the other description, where we really just have abelian groups. All of these are modules, but over different rings a priori. So, yeah. Okay. So another advantage of this description is that if we remember the R module structure, note that we can also explain again how omega n and omega 1 are related, right? Namely, omega n is obtained from omega 1 by taking an exterior power. And I guess here I want to put in this base change to R. And if you do that, then this is the nth exterior power of the corresponding base change to R. Okay, and now we're in business because it turns out this is always, for every polynomial algebra, this is compact projective in mod R. Maybe again a good exercise to check that for yourself. Again, you have to think a little bit about what this omega 1 does. Okay, so we're saying here that we have a composition of two functors. The functor that takes A to this R module, and then the functor that applies lambda n. And it turns out, so what we're really asking for here is, well, if we know that the first functor sends projectives to projectives, then we know that this composition relation, which with saying that this functor is the composite of these two, that sort of extends to the non-abelian derived functors. That's really just the observation that if you take a simplicial diagram of polynomial algebras, the first non-abelian derived functor is just computed by applying this level-wise, but then we're still left with a simplicial diagram of projectives. And so the second non-abelian derived functor is again computed by just applying that level-wise. And that's the same as just applying this level-wise in the first step. So we get that the non-abelian derived functor of this agrees with the composition of these non-abelian derived functors. And if we evaluate them on R, then using the black box, we see that this derived omega n is really the derived lambda n r applied to the object in the non-negative derived category of R given by L omega 1 R, right? So this is where somehow this non-abelian derived stuff becomes pretty powerful, because this might a priori be some complicated complex, but this still tells us what this complex is in terms of this one, but there's going to be some funny additional terms if this guy has higher derived homology. So for example, you can get from that a Grothendieck spectral sequence. If you're interested in the homology groups of this, you can write down a Grothendieck spectral sequence involving the homology groups of this functor and this functor. But keep in mind, these are not ordinary derived functors between abelian categories. So now what should our condition be for this to be concentrated in degree 0? Well, we definitely want it for n equals 1 to be concentrated in degree 0. And then we also want somehow this to not have any higher homology groups when we apply it. And here's a proposition. If L omega 1 R relative Z is concentrated in degree 0, so it's given by a single homology group, which is just omega 1, and omega 1 R relative Z is a flat R module, then L omega n R relative Z is also concentrated in degree 0. Okay, and how does the proof go? Well, the homology groups, all right, since this guy is just the complex omega 1 in degree 0, all we're claiming here is that on a flat R module, the higher this L omega n, this L lambda n is still concentrated in degree 0. And if omega 1 R relative Z is projective, then L omega n R of omega 1 R relative C, L lambda 1 of omega 1 is just omega n of lambda n of omega 1 in degree 0. So that's okay, right? That's just the observation that I guess this maybe you have to check that lambda n commutes with filtered colimits, but then it's really just the observation that on projective guys, my left-derived functor, my non-abelian derived functor is really just computed by applying the original functor. And in general, use Lazar's theorem. I guess there's two things that are called Lazar's theorems. One has something to do with the universal formal group law. That's not what I mean here. I mean the more elementary statement that every flat R module is a filtered colimit of finitely generated projective ones. So if you know that your functor commutes with filtered colimits and takes finitely generated projective ones to stuff concentrated in degree 0, then it takes everything to stuff concentrated in degree 0, because filtered colimits commute with homology groups. Okay, and now we finally can give the optimal version, or our final version of the Hochschild-Costant-Rosenberg theorem, version 3, if this non-abelian derived functor of omega 1 is concentrated in degree 0 and flat. And omega 1 R relative C is a flat R module, then HKR holds. In other words, the Hochschild homology groups are all isomorphic to the groups omega n. Right. And so we're still left with this condition, which still, if you're not used to this whole non-abelian derived functor stuff, maybe looks a little bit daunting. But it turns out that many usual regularity conditions on rings imply that. So for example, if, sorry, I wrote K here, I meant Z. So for example, if R is smooth over Z, then this is always satisfied. But you can get away with weaker notions, for example, int smooth, right? Smooth actually implies that you get projective here, and then int smooth still gives you gives you flat. But this is kind of the right condition. This is precisely what we've used, and then there's some algebraic conditions under which this gets implied. We will see in the next lecture how to think about this in a better way. So this is what's usually called the cotangent complex. Right. And finally, I want to mention that, so we did everything over the integers for simplicity. But it turns out you can actually replace the integers by some base ring k everywhere. And then instead of animated commutative rings, just work with animated commutative k algebras. And you'll see that everything still goes through. Then all the occurrences of polynomial rings just become replaced by polynomial algebras over k. And in particular, this version of Hochschild-Costant-Rosenberg will then involve the non-abelian derived functor of R of omega 1 relative k and say something about Hochschild homology of R relative k. So full generality. The integers here were just for notational simplicity. Okay, that does it for today. Thank you for watching and hope to see you in the next video.